Gas Laws, Part 2, Section 14.2b. We're going to talk first about Gay-Lussac's law. And in Gay-Lussac's, we're talking about temperature and pressure. And we're going to assume that volume stays constant. And as temperature increases, the pressure increases if the volume stays constant. Gay-Lussac discovered this in 1802. And we're talking once again about Kelvin temperature. That's important that we always understand that. We always got to talk about Kelvin. Volume now is going to be our constant. It's not going to change. Okay, so here's our formula. P1 over T1 equals P2 over T2. Take a look at problems on page 43, which I don't have a copy of, but we'll talk about them. Okay, so in the example it says aerosol cans carry warnings on their label that say not to incinerate them or store the cans above a certain temperature. This problem shows why it's dangerous to dispose of aerosol cans in a fire. The gas in a used aerosol can is at a pressure of 103, so P1, 103 kilopascals, and at 25 degrees, so T1 equals 25 degrees. If the can is thrown into fire, what would be the pressure? So we don't know P2 at 928 degrees. So T2, 928. And these are all Celsius. Celsius. So the first thing we need to do is change temperatures to Kelvin. So this would become 298 K and 928 plus 273. 1201. Okay. So then we just plug in. Okay, we know 103 over 298 equals P2 over 1201. Cross multiply. So 103 times 1201. Cross multiply and divide. So divided by 298. And we get pressure 2 equals 415 kilopascals. So you can see it's like 4 times larger than what it was. Alright, why don't you try practice problem number 11. Okay, it says a sample of nitrogen gas has a pressure, P1, equal to 6.58 kilopascals at 539 K. So T1, 539 K. And if the volume doesn't change, what will be the pressure? So P2, we don't know, at 211 K. So T2, 211 K. So if you look, our pressure should be less. If the temperature's gone down, pressure should go down, by over, should be less than half probably when we get all done. So just plug it in the formula. 6.58 over 539 equals P2 over 211. Cross multiply, so 658 times 211 divided by 539 equals P2 equals 257, which is less than half of what it was before. What did I do? 2.57, I think it should be 2.57. Okay. Yeah, 2.57. Didn't get my decimal point in there at first. Alright, so there you go. Now, let's take and put all these laws that we did so far together. And that's the combined gas law. So the combined gas law describes the relationship between pressure, temperature, and volume. And we're going to assume that the amount of gas, or moles, for instance, stays the same. But all the other ones can vary. So the only thing that's constant is the amount of gas. And here's our formula, and this is not written very well. Let me redo it. It should be P1 V1 over T1 equals P2 V2 over T2. These should really have had parentheses around them to make that right. So there's our gas law. Now notice that in all of these, you can create any of the other ones. So let's say that if I want to create Boyle's law, let's do the first one we did. Hey, I just erase my temperatures and I have Boyle's law. If I want to do Charles' law, well, Charles' law, we said pressure stays constant. So erase pressure. And you get that. So you can see how you can get all of them from this. It's all of those same laws. You just, if one of them is constant, we just ignore it and delete it and go from there. Okay, so that's what we were talking about. Take a look at page 424, and let's work through. All right, it says the volume of a gas-filled balloon is 30 liters, so V1 equals 30 liters at 313 Kelvin, so T1 313 K, and the pressure of 153 kilopascals, P1 153 kilopascals. What would the volume be at standard temperature and pressure? Remember, standard temperature, this is P here, standard temperature is 0 degrees Celsius or 273 K. Standard pressure, this would be T2, standard pressure is 101.3 kilopascals, and they want to know, well, what would the temperature be at that point? So I just plug in all the things, P1, V1 over T1. So 153, that's P1. P1 times V1, 30, over T1, 313, equals P2, 101.3, times V2, we don't know, over T2. Now, I am kind of losing labels because it's hard for me to write things that small and get them all fit on this thing. But you should kind of keep in mind all of your labels as you do this. And once again, kind of think of this, hey, we're going to cross multiply. So I'm going to take that, 153 times 30 times 273 equals, the other side, 313 times 101.3 times V2. And then to get rid of this, I would divide by those, 313 times 101.3. Do that on both sides, 313 times 101.3. So I would cross multiply and divide, and so these would cancel, and I would multiply that out, and I'm going to get volume 2 equals 39.5 liters. Alright, why don't you try problem number 13. Problem 13 on page 424. Okay, so put down what we know. Pressure, P1, equals 155 kilopascals. T1, 25 degrees Celsius, and we're going to convert that right away, 273, so 298 K. And the initial volume, V1, is 1 liter. P2, pressure increases to 605 kilopascals. As temperature is raised, T2, to 125 plus 273 equals 398. And V2, well, we don't know that one. That's what we're trying to find out. So, P1, V1 over T1 goes P2, V2 over T2. And just substitute in everything that you've got. So, 155 times 1 over 298 equals P2 605 times V2 we don't know over 398. Cross multiplying, so 155 times 1 times 398. Okay, so that equals 61,690 equals 258, or 298 rather. 298 times 605. 100 and, oops, what did I do wrong here? Clear that. 298 times 605. Okay. 180,290. Okay, so now that's V. Oops. Having some problems here. Okay, there we go. V2. So, solving for V2, I'm going to divide both sides by this 180,000. $61,690 divided by 180. 290. And I get V2 equals 0.34, and we're talking about liters. Now, these are a little harder to kind of reason out, but let's take a look. Okay, the pressure increased, so that should make it smaller. You know, it looks like it's got 4 times smaller. The temperature increased. That should make it a little bit bigger, so it shouldn't be a quarter as big. It should be a little bit bigger than that. And yeah, that's what we got there.